As we all know, irrigation plays a fundamental role in agriculture. For many years, farmers in South Africa have used wind pumps to provide power for their irrigation needs. A bit more recently, solar pumps have also become a popular method of using renewable energy. And it's not surprising, they produce free energy, making them economical and beneficial for the environment. Their only drawbacks: in South Africa, they're still quite expensive to implement and they are very susceptible to theft. A typical farmer in the northwest who has a 170-watt solar pump for small-scale irrigation is fed up with his solar panels getting stolen. He desires to rather implement a low-cost wind turbine to generate direct current to power his borehole pump. The problem is that wind turbines are better suited for large-scale power applications and require high wind speed to fully operate. Potchefstroom has a relatively low wind speed, which impacts the feasibility of installing wind turbines in the area. So the engineering problem is that a small-scale farmer wishes to install a wind turbine to operate on the low wind speeds of the northwest and harness the majority of the daily winds encountered. This wind turbine must provide regulated electrical power to pump water from a borehole into a storage tank. A statistical analysis showed that the turbine must be operational within a wind speed range of 2.2 to 4.1 meters per second to harness 80% of the average winds encountered. The solution is implemented as follows. The electrical power generating component is a 250-watt brushless DC motor directly coupled to the turbine's rotor hub. This motor is integrated by designing mechanical parts to secure it to the tower and the rotor. An important aspect of the system is the power storage device. All generated energy is temporarily stored in a battery bank. This allows even the small amounts of energy generated at low wind speeds to accumulate until there is enough available to drive the pump. The power generated by the turbine is rectified and regulated by a buck and boost converter to supply a steady voltage to charge the batteries. An Arduino measures the voltage across the battery bank and connects it to the pump when fully charged. The Arduino also controls a process called electrodynamic braking to prevent the turbine from overspeeding in strong winds. A system evaluation proves that the turbine operates in wind speeds ranging from 2.25 meters per second up to 5.4 meters per second. In this range, the turbine can generate 30 watts to 407 watts of power respectively. When the turbine operates at its maximum rated wind speed, the batteries will fully charge within 18 minutes. The battery bank runs the pump for about 34 minutes per cycle, which pumps roughly 1,700 liters of water into the tank for later use.